Okay, yeah, so please, Marco, yeah, whenever you're ready.
Okay, so we're doing the third part now of a four-part series on GC geometry, generalized complex geometry. Um, okay, so well, let's look at what we did last time. So last time, um, there's there's a couple of key calculations. One of them is well, okay, so first thing that you have to absolutely remember, and I just recall it now, is that if you have let's say you have a complex structure I, you have a complex manifold, and if sigma is a uh, is a section of wedge 2 0, sorry, I'll put it this way, wedge 2 of T10. So if it's a bivector field of type 2 0, and if d bar sigma is equal to 0, meaning that it's holomorphic, and if sigma bracket sigma is equal to 0, this is what we call a holomorphic Poisson structure in the usual like study of Poisson structures in the complex manifold category. Okay, and then we can take this holomorphic Poisson structure and we can write it in terms of its real and imaginary part. And this Q, so the relationship between the real and the imaginary part is dictated by the fact that it's of type 2 0, and it means that P is Q composed with the complex structure. So basically, the Poisson structure is determined by the imaginary part and the complex structure itself. So that's why this generalized complex structure here, it contains all the information of the holomorphic Poisson structure. Okay, now the idea, I mean, the important thing to comment on, the important thing to remember is that given a holomorphic Poisson structure, you can extract Q and place it here, and that will give us a deformation of the GC structure. When I say it's a deformation, because you could take Q to be 0, and then that would be a complex structure. But then if Q is non-zero, then it will be a generalized complex structure. And I'm going to talk in a few minutes about deformation theory of generalized complex structures, because that's an important part of the theory. But anyway, we have here a rich source of generalized complex structures, namely the ones that are coming from holomorphic Poisson manifolds. So any holomorphic Poisson bracket gives you an example of a generalized complex structure, and then you could take that thing and you could change it or modify it and produce other examples. And we'll get to that in a minute. Okay, so that's the main source of exotic generalized complex structures. What I mean is, it's very easy to find symplectic examples, complex examples, but then the things that are in between, um, you can access them by studying this holomorphic Poisson geometry. Okay, the other thing I want to take from the previous lecture is this observation that let me see, yeah. So it was just a conjugation. So the idea was, suppose you start with a generalized complex structure of the holomorphic Poisson structure type, and then you apply a B-field transformation. So you just pull it back by a symmetry. Can you change the look of the matrix? And the remarkable thing is that if you choose the B field appropriately, you can kill the diagonal parts of the matrix, and you can get one of these off-diagonal terms, which means that it would be a symplectic structure. Okay, and in order to be able to do this, we needed the B field to satisfy this equation. And in other words, we needed Q to be invertible, and as long as that's true, we can do this. Okay, so what does this mean? This means that any holomorphic Poisson structure, so you could have a holomorphic Poisson manifold, okay, there might be a region in that manifold where Q is invertible, where the Poisson bracket is non-degenerate. It doesn't have to be the entire region. It could be just, it doesn't have to be the whole space. It could be just an open set inside the space. And in that region, Q is invertible, therefore there exists a closed two form satisfying this. You could just solve for B, you just invert Q and compose with I. So this two form will exist in that region, and we can apply a B-field transform to the structure in that region, and then it will be equivalent to a symplectic structure. Okay. So if you happen to be in a case where you're so for example, let me put this in red because it's important. For example, if I is part of a hyperkähler structure, IJK, then we can what you can do is take the complex structure and then take the Poisson structure to be omega j plus I omega k inverse. This is the famous holomorphic symplectic structure of I. So on a hyperkähler manifold, every complex structure has a corresponding holomorphic symplectic structure, and if you take that holomorphic Poisson structure, then you'll notice that it's non-degenerate everywhere. So on the entire manifold, okay, so let me just, so based on previous observation that this is equal to Q inverse Q, when B is equal to minus Q inverse I, okay, we conclude that on a hyperkähler manifold with so a hyperkähler manifold, it consists of a Riemannian metric with three compatible complex structures. So it's Kähler in three different ways, and where I j is equal to k. These I, j, and k, they satisfy the quaternion relations. So a hyperkähler manifold is like having three different Kähler structures which all share the same metric. I'm sure that you all are somewhat familiar with these hyperkähler manifolds. But on this hyperkähler manifold, we have I and sigma, as I just said, omega j plus I omega k inverse. This is holomorphic Poisson, and it's non-degenerate. Okay, and so that means that if I take this IQ minus I star, this is equivalent as a GC structure to Q inverse Q, symplectic structure. Okay, and this thing, letting Q go to 0, we see that this is a deformation of complex structure, I 0, 0 minus I star. Okay, so this means that we have a picture. We can draw the following picture. We can say that there's a space of generalized complex structures, and we can see that there's some special locus of complex structures. Okay, and then you can deform. In other words, you can create a path, let's say by letting Q go to TQ. Right, so if we let T be some complex number or real number, we can turn on Q. We can travel away from the complex locus in the moduli space. And we can end up in some locus where it's of symplectic type. So what this means is that the symplectic and complex moduli spaces are actually contained or embedded in the moduli of generalized complex structures. Now, I mean, I haven't defined the moduli space of complex structures, but I'll do so in a few minutes. Okay, so this is giving us kind of a large collection of interesting spaces that we can think of in terms of generalized complex structures. And the thing I just want to, the second example that I want to give, so this is the first thing is about hyperkähler manifolds, but the second thing is about holomorphic Poisson manifolds. For example, suppose that we took a complex surface, CP2, and suppose that we chose a holomorphic Poisson structure. Holomorphic Poisson structure. In this case, any section of wedge 2t will do because wedge 3t is 0. But this wedge 2t, this is just the O3 line bundle. And so this is a section of O3, which means that it's a cubic polynomial. So, and this is a line bundle. So a Poisson structure on a complex surface is just a section of a line bundle. It's an unconstrained section, holomorphic section of a line bundle. And so that section is either 0 or it's non-zero. And so that means that the rank as a bivector is either 2, where sigma is not 0, or it's equal to 0, where sigma is equal to 0. So the rank of the Poisson tensor can either be 0 or 2, depending on whether you're on the 0 locus or not. Okay, and so the picture here is a picture of the manifold CP2, and you have inside here you have a curve where sigma is equal to 0. Sigma is equal to 0 is a curve that looks like this. It's a cubic curve, and everywhere else it's non-degenerate. So here it's non-degenerate. Sigma is non-degenerate. And so what this means is that in this whole region, in an open dense set, in the non-degeneracy locus, the GC structure is equivalent to a symplectic structure in this blue region. But then here on this degeneracy locus, the GC structure is just I 0, 0 minus I star, because Q is equal to 0. And so it is of complex type. Okay, so this is an example of type jumping, where we go from something that has symplectic type, which is type 0, to a complex surface, which is type 2, because it's two-dimensional complex. Okay, and you can see that yeah. So if you were just at this specific point, a point on the cubic curve, then it would look on that t plus t star, it would just look like a complex structure, and here it would look like a symplectic structure. So you can see that on the same manifold, the geometric structure can switch, and so it's not locally trivial, as we discussed before. So the local normal form that I prove with Bailey is basically saying that in these points, it looks like just a symplectic structure. And at these points, it looks like a Poisson structure on a complex structure, on a complex manifold, a complex surface, where the Poisson structure vanishes at this point. So you would get there's only two local normal forms involved in this example. There's exactly two distinct local normal forms. So you could think that the whole thing could be covered by an atlas of charts, each chart being one of these two local normal forms. The one local normal form is, you could say it's R4 with the standard symplectic form, and the other one is C2 with sigma is equal to x d by dx wedge d by dy. So here you see you have a complex manifold standard, and you have a Poisson structure, holomorphic in the two variables x and y, which vanishes linearly at the origin. So these are the two local normal forms. You could take these things, glue them together on overlaps, and describe the entire structure if you wanted to. Okay, questions?
Yeah. Well, I have
Before
one
go on.
question.
Yeah.
What is the difference between Q and sigma? I don't know if you're using the same.
Q. So sigma is P plus IQ.
Okay.
That's all. So this remember that this operator is always real. It's a real transformation of T plus T star, and so only the real stuff has to occur here. But sigma is holomorphic. It's killed by the D bar operator.
What is P?
Well, P is the real part. P is the real part. But this thing is a holomorphic. Sorry, 1 second. This is a section of wedge 2 T10.
Okay.
So it has a specific type, like a 2-0 type. And that implies that to travel between P and Q, you have to use the complex structure. P determines Q, Q determines P. And a better way of writing it is you could write it like this, that it's I after Q plus little I times Q. So the real part is the same thing as the imaginary part, post-composed with the complex structure.
Okay.
Or you could think that one of the indices is that's what it is. That's what it is.
Thanks.
So the point is that whenever you have a holomorphic Poisson structure, there's two distinct real Poisson structures underlying it, the real part and the imaginary part. Those are two different real Poisson structures. And they have the same rank at every point, but they are different. And they're related by the transformation of the tangent bundle, which is the complex structure itself. Any other questions before I go on? So this is giving you a gigantic, a huge family of generalized complex structures. I can even, well, it's okay. I'll resist the temptation to give you more examples of these at this point.
I'm sorry, I have a question about this local picture.
Yeah.
I'm just struggling to see how does it work if you start with a cubic polynomial which has a nodal point.
It doesn't really matter. Any cubic polynomial is a section of wedge 2T, and therefore it is a Poisson structure. It will have an imaginary part, so you put the imaginary part here.
But yeah, I'm asking rather about this local structure which you gave for GK.
Yeah, the local structure would only be valid for smooth. So if the point is smooth.
Okay, thank you.
Okay, but actually, the local normal form says that, I mean, if you have any kind of singularity, right, then what that means is that you're providing a germ of Poisson structure which is not isomorphic to this one, right? To the x d by dx d by dy, right? So in fact, any if you take the germ of a curve in the plane, right, that always defines a Poisson structure, a Poisson bracket, and all those germs of curve singularities, if you want, they're all distinct Poisson structures, and they are all distinct GC structures. So the theorem says that they're in one-to-one correspondence with germs of holomorphic Poisson structures. So basically, there's as many local GC type jumping structures on in 2 dimensions as there are curve singularities. but the curve is, it's not enough. It's not just determined by the curve, because the Poisson structure, if you think about it, this Poisson structure here determines a curve, namely where x is equal to 0, but where that curve vanishes, it will induce a vector field on this curve. So there's something called the modular vector field. So anyway, the Poisson structure is determined not just by the 0 locus, but also by a certain data. There's certain data in the neighborhood of that 0 locus, which you need to keep track of. So anyway, there is no, as far as I know, the problem of classifying holomorphic Poisson structures up to isomorphism has not really been treated. So it's not. It's only in certain cases that that I've looked at, or that my student Brent Pym has looked at, where we get some classification results for holomorphic Poisson germs. And there's a lot of work, however, that has been done on classification of global Poisson structures. That's for some reason that is viewed as a much more interesting problem. I don't know.
Sorry, Marco, can you repeat? I think what you just touched on there, like you
Yeah.
said
So this is one of the this would be like an open problem, which touches on holomorphic Poisson geometry, which is to classify germs of Poisson structures at a point in the holomorphic category. Okay. So this is a it's a problem that would be very, I mean, it's a very interesting problem, and it has to do with it should be attacked by someone who is interested in Hironaka resolution of singularities, because although the germ is smooth, like it's a Poisson structure near a point on a smooth manifold, but the point is that that Poisson germ can be desingularized, right, by the symplectic groupoid, and so you're really talking about maps. So there's a symplectic groupoid, which is a smooth space whose Poisson structure is non-degenerate. And so all of the complications of the degeneracy loci and all that, they're all incorporated into the map, which maps from the symplectic groupoid down to the Poisson structure. And so you're really studying singularities of maps, right? So the spaces are smooth, but the map, you can encode the Poisson structure in a map, a holomorphic map, and it is the properties of that map which basically govern this germ. And so it would make sense for people who are interested in the singularity structure of maps to investigate this. Yeah, so that's an open problem. And that open problem kind of comes from this as an outgrowth of this result. So, we need a classification of these if you really wanted to classify. Okay, but the question is classification up to what? Okay, it could be that depending on the situation, you could imagine that there's no reason, it's not clear that the moduli problem is well posed for this issue, but and that's what people often say. But in the holomorphic category, it might be well posed. It probably is a nice classification problem. It's just that in the real category, it's because of the failure of ellipticity, it's badly behaved. Anyway, so that's maybe I'll highlight it in purple for open problem.
And can I ask something else? I guess
Yeah.
you mentioned I didn't fully get it, but I think you mentioned that for these holomorphic Poisson tensors, you have some canonically associated vector field on the vanishing locus.
Yeah.
I'm not familiar with this. What is it?
So I've called it. Well, I've mentioned it in a few of my. I've used it in a few of my papers, and in fact, when you do the generalized scalar flow construction, So
Yeah.
there's a vector field. In order to construct a GK structure on CP2, you can do it by this holomorphic flow. Excuse me. You can do it by the flow construction.
Mhm.
That's in my non-commutative brains paper. And this flow construction involves a vector field. And that vector field is not holomorphic on CP2 or on a complex surface. It's a real vector field, but it's not holomorphic. However, the vector field is tangent to the zero locus. The vector field that you know is tangent to the zero locus. And on the zero locus, it is holomorphic. And it generates a translation of the elliptic curve. This is called the modular vector field. And it's defined in a really simple way. Like, for example, if you had x d by dx, wedge d by dy, this vanishes on x equals 0. And where it vanishes, I can take its derivative. If you differentiate it, you're going to get dx tensor del x wedge del y. Okay, you can use a connection if you want, but the point is that whenever you differentiate a section, that derivative is uniquely defined where that section vanishes. So here I'm just restricting to x equals 0, and you get this. And then you can contract this, you can trace it out, and you'll get d by dy. And this is a vector field that is tangent to x equals 0. And this calculation holds more generally for any Poisson surface. So there's a natural vector field, canonical vector field there. Another way of doing it is by actually I kind of prefer doing it in the more standard way, where you take the Poisson structure and you invert it and you get a logarithmic symplectic form, and then you just take the residue.
Oh.
And the residue will give you a 1 form defined on the 0 locus. Because this thing here is a logarithmic 2 form, right? This is a logarithmic 2 form when you invert it. And when you take the residue, you'll get a 1 form on the curve. But this is an elliptic curve, so the 1 form is non-vanishing, and so you can invert that 1 form to a vector field. And that's what gives you this thing.
But you're saying more generally, you literally just you choose somehow any connection, and you do what you said, you differentiate and contract, and
yeah, and that will be independent. That will be independent of the connection, as long as you're at a 0 set of the section, right? Because if you think how a connection acts on a section, it's derivative plus a times s, right? So where s is 0, that extra term goes away.
Yep. Yeah. I see. And again, just so I'm sure I didn't lose anything. I mean, this is not actually special to 4 dimensions, right? This is.
Yeah. However, there's a whole there's a whole tensor calculus of various invariants that you can extract from a Poisson tensor in higher rank. Basically, it's basically like a residue calculus. So you can imagine if you had a real 8-dimensional space where you had a Poisson structure, like on CP4, let's say. You could have a holomorphic Poisson structure on CP4. Invert that's going to be it won't be a logarithmic 2 form, but it will be like it will still be like a singular 2 form, a 2 form which is logarithmic most of the place. It'll have worse singularities along higher codimension, but you can extract a residue of that, and that will be a volume form on the hypersurface where it degenerates, and that volume form will make it into a Calabi-Yau manifold. So the 0 locus here is an elliptic curve, but in the complex dimension 4, it would be a Calabi-Yau threefold. So that seems to be important, especially. Yeah. Okay. And let me just say briefly, I don't want to go into this because it's not really that useful at the moment. But using the above examples, we can construct examples, GC examples, GC manifolds, which admit neither complex nor a symplectic structure. So you see, the example that I gave was that of CP2. Okay, but CP2 we know that it has a complex structure to begin with, and we deformed that to get this example. And we know that it also has a symplectic structure. So in a way, people might be less impressed because you just started with CP2 and you deformed it. Anyone can do that. Okay, but maybe what you should do instead is you should focus on this degeneracy region, and you take a tubular neighborhood of it. Okay, and then you just excise this tubular neighborhood. Oops. So you just excise this, and you're left with a tubular neighborhood of a type change locus. So this is going to be, roughly speaking, this will be like a disk bundle over 2 torus. Okay, and now what you do is you look for some interesting symplectic 4 manifold, and you look for a certain a symplectic T2, or you can even do this with a Lagrangian T2. There's an alternate construction, and you try to find one that has its own tubular neighborhood. Okay, which is such that the tubular neighborhood minus the curve and the tubular neighborhood minus the curve, the torus, I mean, the torus, are symplectomorphic. Okay, I hope it's clear what I mean. Of course, this cannot be symplectomorphic to this, because this has the symplectic form is blowing up here, and you're getting something which is not symplectic at the curve, at the T2. But away from the T2 in this punctured disk bundle, and this punctured disk bundle, you try to find them so that they're symplectically isomorphic. That's not so difficult. And then what you can do is you can then glue, you can replace the right disk bundle by the left one, and we get a generalized complex 4 manifold. And this is not a deformation construction. And by doing this, in my papers with Cavalcanti, with Jules Cavalcanti, we painstakingly proved that this procedure can produce examples of 4 manifolds which are neither complex nor symplectic. Okay, but in recent works of his and his students, okay, he's developed techniques which get around all of the painstaking details that we had to do to prove these things. And now he has a way of proving it really easy. So it's very easy now to see that you can get all kinds of GC structures that are not GC manifolds which are not symplectic or complex. I don't want to give the details. The important thing is to get the idea. It's a surgery construction. You take out a neighborhood of the type change locus and you plug it into another symplectic manifold, which you find by just searching. Okay, so let me now get to the main thing I wanted to talk about today. Um, okay, so okay, so we saw before that a generalized complex structure is determined by a pair of complex conjugate Dirac structures. This is a generalized complex structure on the manifold M together with a closed three-form background. Okay, and L and L bar. So these are the plus I and minus I eigenspaces, eigenbundles of J acting on Tm. So so let me draw that, these two maximal isotropic bundles, L and L bar. Okay, now whenever you have, so this is an example of what's called a Manin triple, where you have a pair of transverse Dirac structures. Okay, it's a really important type of structure. It's kind of like having, like I said before, having a Dirac structure is like having a foliation, and having a pair of Dirac structures is like having a pair of transverse foliations. Anyway, let me explain what happens here in this case. So because we have this inner product on Tm, and because L is isotropic, right? What that means is that when we take the pairing of L bar with L, okay, there's a perfect pairing between L and L bar, meaning that, you know, if I take an element inside L bar, and if I, let's say A, and if I look at this covector, this will be non-zero on L, and this establishes an isomorphism between L bar and L star. So using the pairing, L bar is isomorphic canonically with L star. And so it implies that this generalized tangent bundle, which is T plus T star, can actually be written as L plus L star. Right? So this is kind of the reason why these Manin pairs are important. It's because it gives you a kind of different basis with which to write the courant bracket, the courant algebroid. Okay, and okay, so that's interesting. So let's see what we can. This gives rise to a certain algebraic structure, which is called a Lie bialgebroid. Okay, and this whole topic of Lie bialgebroids, it was developed again by Weinstein and his students, and it was developed in analogy, although the algebroid case is much more interesting, with stuff that Drinfeld studied when he was studying Poisson-Lie groups and quantum groups. So he studied and classified Lie bialgebras, and those are very important for the study of quantum groups. But so these are the direct analog of that in this algebroid case. So this is an analog of Drinfeld's Lie bialgebra for quantum groups. Okay. Anyway, This algebraic structure is pretty simple. Let me just explain what it is. So because L is a Lie algebroid, okay, we know that it behaves like the tangent bundle, and so the exterior algebra of the dual, if we take sections of that, this has a differential, and we get a de Rham complex. Okay, and but so this means that the relationship, the obvious relationship between L and L dual is that L dual is like the one forms on L, and it has a differential which goes to 2 forms and 3 forms and so on. Okay, but this is always true anytime you have a Dirac structure, that the Dirac, and this will have a cohomology, which is called the Lie algebroid cohomology. But because L bar is equal to L dual, this means that L dual also has a bracket, because L bar has a bracket. L bar is a Dirac structure. So this is an unusual situation where L star is actually embedded as a Lie algebroid, as a Dirac structure, and so it has a bracket. But now L star, which is equal to L bar, also has a bracket. So now what we have is the de Rham complex, the de Rham complex with a differential. So that's a differential graded commutative algebra, but it also has a Lie bracket coming from L bar. And this is a graded Lie bracket. Okay, and not only that, but it is compatible with the differential. DL is a derivation of the Lie bracket. Okay, and so this whole thing is a differential graded well, see, you would like to say that it's a differential graded Lie algebra, and that is true. You would like to say that it's a differential graded commutative algebra. That's also true. So it has both commutative and Lie structure. So together, this means that people just got tired and they just gave it a different name. So it's a Gerstenhaber algebra. Okay. I hope I'm not differential graded. Yeah, that's right. That's right. Okay, but okay, any questions so far? All I did was use the pair of Dirac structures. I'm saying something which is not obvious. You need to check that this is a derivation of this bracket. It's not difficult, but it's not obvious. Any questions about this? So, whenever you encounter a DGLA, that should be a sign to you that, well, what is a Lie algebra? Well, a Lie algebra is infinitesimal symmetries. That's what a Lie algebra is. Okay, but what about differential graded Lie algebra? Well, this means that it's higher symmetries in a way, because it's graded, and there's like grade 0, which is symmetries, and then grade 1, which is who knows what, some kind of generalized symmetry, and so on. And that is really true, because if you think about what is a higher symmetry, well, in a way, you should think that a higher symmetry is like saying that, like, what does it mean higher? Well, one way to interpret this, which is accurate, is that an infinitesimal symmetry is like a symmetry on every open set. And a higher symmetry is like a symmetry on every overlap between open sets. And an even higher symmetry is a symmetry given only on triple overlaps, and so on, which is coherent right? So what does it mean in this case? If you give me an infinitesimal symmetry on overlaps, right, ui intersect uj, what are you doing is that you're giving a symmetry not of the original structure, but you're giving a symmetry which modifies the gluing between the local pieces of the structure. And so what you're doing is you're deforming the structure. So deforming a structure is just a higher symmetry, a higher ordered symmetry. That's how you should think. I'm told that is the modern way of thinking. So there you go. Anyway, so this is a clue that this is the structure. This is the algebraic structure that we should use to study symmetries and deformations of generalized complex structures. So this is the DGLA used for studying symmetries of GC, i.e. Generalized holomorphic vector fields, and deformations, which are one symmetries, if you want, of generalized complex. Okay, so whenever you have a differential graded Lie algebra, you need to, so in order to find deformations, so as is always the case, as always, deformation, so an infinitesimal symmetry is something in the in the 0 degree part of the Lie algebra. And because it's differential graded, you want to impose that it's closed. So dA is equal to 0. And in order to be an infinitesimal deformation, we need something to be in L1 with dL. I'll call it epsilon, or actually I'll call it E. And we need this to be closed. So this is how we find infinitesimal symmetries and infinitesimal deformations. But actually the differential graded Lie algebra, this will be the sections of L star, except that I need to shift the grading so that it's just like in the tangent bundle for the multi-vector fields, that among the multi-vector fields, the ones that actually form a Lie algebra are the vector fields, which means that they're the degree 1 part of the multi-vector fields, of the polyvector fields. And so degree 1 is really degree 0, because that's the thing that's a genuine Lie algebra. And everything else is a graded Lie algebra. So you really need to subtract 1 here in order to get what I'm talking about. So this means that you're going to have omega 0 L, that's going to be in degree -1, omega 1 L, that's going to be in degree 0, and omega 2 L is going to be in degree 1, and so on. So this is the Lie part, and the differential will go like this. Okay, so this is where we have our symmetries. This is where we have our deformations. Okay, and infinitesimal deformations are well and good, but an actual deformation is given by a section of L1 which satisfies a nonlinear equation. So the Morat-Cartan equation is 0, the Morat-Cartan element corresponding to E. So the Morat-Cartan equation is this. You take dLE, but you also take the bracket of E with E using the L bar. And this will be in a section of wedge 2 L star. So we want this thing to vanish. This is the Mohr-Cartan equation. Okay, and the nice thing is that there's a very clean geometric interpretation for this, which is that if we look at the picture of L and L bar, we notice that epsilon, okay, epsilon is in wedge 2 L star. Oh, I'm sorry, I got the grading screwed up. When I take dl of epsilon, epsilon is supposed to be of degree 1, which means that it's in wedge 2 L star. And then if I apply d to it, it'll be in wedge 3 L star. Okay. But if we have a deformation in wedge 2 L star, this can be viewed as a map from L to L star. Sorry, let me write it. Epsilon defines a map from L to L star, which takes something and hooks it in to epsilon. And so we can take the graph of epsilon. We can take this this map and look at its graph. Okay, and this this graph is supposed to be the plus I eigenbundle of the deformed. So this is supposed to be the plus I eigenbundle of the epsilon deformation of the generalized complex structure, right? And in order for this thing to be a genuine deformation, what we need is that this graph is involutive. And if you write down the involutive condition, you get exactly this. So it comes down to the bracket. It comes down to the Lie algebroid differential and the bracket on the L bar part. So the Mohr-Cartan equation is exactly the involutivity of the graph of epsilon. Okay, and then once we have deformed L to the graph of epsilon, we take L bar to be the graph of epsilon bar. Okay, and this might be a problem. So there's a warning here. Okay, the warning is that if epsilon is too large, it might be that graph of epsilon intersect graph epsilon bar is not empty, is not zero. Okay, so if you take the graph, if this graph goes too far, okay, then when we take the complex conjugate, let me draw the complex conjugate. Why not? Graph epsilon bar. Okay, so it could be that this graph is so large that it will have an intersection with its complex conjugate, and what that means is that you've deformed it as a Dirac structure, but not as a generalized complex structure. So you're kind of you have to remain in a small open set around L in order to have this type of this algebraic description of the deformation space. Let me just do one example, and then I'll ask for questions about the deformation theory. So the remarkable fact, in contrast to the real category, usual man in pairs, is that this differential graded algebra, this thing is elliptic, meaning that this is an elliptic complex. And so this implies that the cohomology groups on M compact are so it means that on M compact, the dimension of the cohomology groups for this operator are finite dimensional. Okay, and so yeah, and so this operator is really yeah, it's somehow telling you that there's some interesting things to compute here that are kind of captured by the geometry. So those are, you know, those could be invariants associated to the manifold, to the foliation, to the symplectic form. You know, there's all kinds of possible information that could be captured in this cohomology. All right, so so let's just do an example. So the example is the simplest one. Let's say that we just have a let's say we begin at a complex manifold Mi. Then remember that J was I minus I star. Remember that L was T01 plus T star 10. And that L star is equal to L bar is equal to T10 plus T star 01. And so that means that the exterior algebra on L star is the exterior algebra of this direct sum. And so it's the tensor so in other words, it's the exterior algebra of T10 tensored by the exterior algebra of T star 01. Or in other words, it's the Dolbeault complex of the holomorphic multi-vector fields. Okay, and so the way that the deformation theory works, I'm just in case there are some students here who don't know how that looks. In the deformation theory, we have all the solutions to Maurer-Cartan equals 0 modulo symmetries generated by dl epsilon equals 0. Remember, I said that the closed elements of this complex would give us symmetries. So we need to take deformations modulo symmetries is some space, some finite dimensional space because of the ellipticity. So this is the moduli space. And we have a point, which is the original complex structure, I. And if we were interested in the tangent space to this space, the tangent space to the moduli space at the complex structure, okay, what that means is that this space consists of solutions to the Maurer-Cartan equation, solutions to this nonlinear equation, right? But if I want the tangent space to the space of solutions, what I do is I have to take the tangent space to the solution space. But the tangent space to the solutions of a nonlinear equation is the space of solutions to the linear approximation to the equation. So what you do is get rid of this term and just have this term. Okay, and you're looking at closed two forms, modulo exact two forms. So it turns out that the tangent space to the moduli space of solutions to this equation is the cohomology in degree 2, because epsilon is in degree 2. So this tangent space is equal to the second cohomology of this space. Now, you have to be careful that this this moduli space may not be smooth. Okay, and that's what I proved in my earlier papers, is that there's an analytic obstruction map from this finite dimensional vector space to let me call it I to no, sorry, I'll call it nu to H3 DL. So the thing that I proved is that there's a map, a holomorphic map, essentially an analytic map from this vector space to this vector space, which if it vanishes completely, that means that this moduli space is smooth. Let me leave it at that. I proved some more complicated stuff, but it's not that important. There's some kind of criteria for determining whether this space is smooth. Nevertheless, if it has this tangent space, and so we can compute the tangent space. I'm going to compute the tangent space to the moduli space of GC structures at a complex structure. This will be H2 DL, which is going to be H, the cohomology of this thing. So it's the Dolbeau cohomology. So it's the sum where P plus Q equals 2 of HP, I'll put it HQ of wedge PT. All these Dolbeau cohomology groups of the tangent sheaf, or the exterior products of the tangent sheaf, the ones that sum up to 2, those form the tangent space. And so there's only 3 spaces here. There's H0 of wedge 2T, there's H1 of T, and there's H2 of O. Okay, and I just want to point out, so here we see the usual deformations of complex structure. So there's a certain direction in the tangent space, which is the usual complex moduli space, which then would integrate to a curved moduli space of complex structures. Okay, that's the usual moduli space of complex structures that is studied, for example, in the famous book of Kodaira, Deformations of Complex Manifolds. That would be this green stuff here. Okay, but then there's this this stuff here, which are deform the complex structure by adding a holomorphic Poisson structure. We studied this. So it becomes IQ minus I star, right? And we know that generalized complex structures can be deformed in the Poisson locus. Okay, and finally, there's this other third part, which are called the B-field transforms. Okay, and so there's some other direction here where the complex manifold can be deformed by doing these are basically conjugating by a B-field. It's roughly speaking, this is conjugation by a cohomologically non-trivial B-field. Okay, and so all of these are unified in the deformation space for the GC structures. Right. Okay, and the other thing the last thing I want to comment about this is that this was surprising to see at the time. at the time that GC structures were invented, since this is the tangent space to the deformation space of the so-called B model, which is a quantum field theory associated to a complex manifold. Okay, so the idea was that they were studying the B model. It's a very famous quantum field theory defined by more or less defined by Witten in I don't know, I guess it's in 92 or something, shortly before Kontsevich came up with homological mirror symmetry. Witten defined two topological quantum field theories, one the A model and the other a B model. A model is associated to a symplectic manifold, B associated to a complex manifold. And the point is that the quantum field theory had certain moduli, had certain parameters that could be varied, and it makes sense to study the deformation theory of a quantum field theory. It's some kind of mathematical model that is built from the complex manifold. And it turned out that there were exactly these deformations of the quantum field theory. And so it became clear that that the generalized complex structure was kind of seeing in a geometric way what the meaning of those deformed quantum field theories actually were, so that it's instead of saying, which is what they would have said before, they would have said, if you deform the QFT by one of these directions or one of these directions, then it fails to be geometric. It's now a non-geometric QFT because it's not mapping into a complex manifold anymore. It's deformed into the space of QFTs. But it turns out that that's not quite the case, that the geometry actually does deform, and that we get this correspondence between quantum field theories and generalized complex structures. Okay, I'll leave it there. Any questions? I have some time. I just don't want to go as far over as last time.
So like using this description of deformations, is it easy to write one down that sort of isn't just this sort of deformation by Poisson structure? I mean, this is sort of the only kind that I really understand, I think.
I mean, this is only the deformations at a complex manifold. So if you were at a complex manifold,
Sorry, right, yeah.
right? I mean, the deformations that you can easily do are deformations of the complex structure itself. So that would be like in the case of K3 surfaces, there's a complete Torelli theorem, and so you can just take the point, you can just take the period and move it, just change the period, and that would be moving in this direction. But then you could also turn on that Poisson holomorphic symplectic form, and that would take care of this. And you could also do these B field transforms, which is like we said before. You could just apply a B field transformation to the generalized complex structure. And so what you end up in the case of a K3 surface, this is isomorphic to the idea of period maps is that basically this differential graded Lie algebra becomes isomorphic to some complex associated to the de Rham complex. So on a K3 surface, instead of dealing with vector fields or multi-vector fields, you can use the fact that there's a volume form to kind of convert any multi-vector into a form. And so it just becomes regular cohomology. And so this becomes, this part becomes the H1 of omega 1. So on a K3 surface, the you can sorry, what am I saying? Yeah. Yeah. Sorry, what am I saying? Right. Let me just draw the Hodge diamond of a K3 surface. Okay. So here's dimension 0, 1, 2, 3, and 4 on a K3 surface. Okay. K3 surface is holomorphic symplectic, so it's a hyperkähler, so it's a good example of everything I said before. If you look at the H11, so H1 omega 1 is isomorphic to H1T for a K3 surface, because T is isomorphic to omega 1 on a K3 surface. And so that means that the complex deformations are of dimension 20. Okay, but then you've got an additional an additional H0 of wedge 2T that's sitting right here. That's a one-dimensional space. And then you've got an additional H02, which is sitting right here. So in total, you would have a 22-dimensional space. And it turns out that this is completely governed by a period map. So that means that if you vary the period, but you vary it in this larger second cohomology with complex coefficients, in other words, you can move it in any direction, not just in H1 omega 1, that will be a deformation of complex structure. This is the basis of that paper by Huybrechts, where he talked about generalized Calabi-Yau structures on K3 by Huybrechts. Okay, that's what he's observing. He's observing that the same period map for K3 surfaces actually extends to generalized complex K3 surfaces. And that gives you a combination of all three types. You can deform in a way that is neither complex, nor B-field, nor Poisson. It's some combination of all three. And I guess, on a hyperkähler manifold, you can obviously you can do the same. You can do a similar thing. What I mean is that there's this hyperkähler Torelli theorem now, and so we can use that and generalize it. I've been wanting to extend Huybrecht's paper to the hyperkähler case for a while. I'm hoping that one of my students would be interested in this. But anyway. Does that help? Or
yeah, thank you. Yeah, no, that's
yeah. And,
So what,
I guess.
Sorry, I think Mario has a question.
Oh yeah.
no, but go ahead. You were saying.
Well, I was just going to say that this cohomology invariant for example, in the case like this, where you glue a generalized complex structure out of pieces, okay? So you're gluing a GC structure out of pieces. You're getting an exotic GC structure. It has nothing to do with a complex manifold or a symplectic manifold. Nevertheless, by the theorem, and these are compact, let's say. So by my theorem or whatever, ellipticity, that there's a finite dimensional cohomology theory associated to this thing. And you can actually compute it very straightforwardly because you have an open cover of this manifold, and you can use like Meyer-Vitoris. Okay, so these invariants are even in the case where the manifold is not complex or not symplectic, right? So something very unfamiliar. You can't use Dolbeau cohomology. You can't use a spectral sequence that converges from something that you know already to compute this Lie algebroid cohomology. Nevertheless, you can actually compute it. So we and so the question, you might, there's this is an open problem in the sense that like we don't really know what this cohomology really means, right? Dolbeau cohomology is related to sheaf cohomology, and it's related to so many important things in sheaf theory and so on. This would be an analog of that. and in the symplectic case, you know that the symplectic structure affects the cohomology very much because of the hard Lefschetz theorem. So the cohomology of a symplectic manifold is very highly constrained. There's works of Donaldson and his students from the early days about this, or not that early, but like Oru and so on. And there's also results by Cavalcanti, for example, about computing the cohomology ring structure for symplectic manifolds and finding like certain things about them that is special to symplectic geometry. So similar things should be true here. So there's very little known about this DGLA and you know how it relates to the underlying geometry. But anyway, yeah, sorry. Go ahead.
Yeah, I have two questions. One is what happens if your GCS comes from a symplectic structure? Do you get like the space of deformations of the A model, or?
Yeah, it will be the deformations of the A model, which so the deformations of the A model. So deformations of A model of a symplectic manifold. This will be H2 of M. But the interesting thing, the thing that was always interesting about the A model, is that it's H2 of MC, which means that you're deforming omega, let's say omega plus some delta omega, but you're also introducing an imaginary part or a real part, another two form, which is the B field. So in fact, the A model is defined for a manifold together with a symplectic form and a closed two form, whose so in the symplectic form, yeah, it depends heavily on the symplectic form, but it doesn't depend heavily on the two form B. It only depends on the class of B in H2M R mod Z. Okay, and whereas it really depends on the details of the symplectic structure, not just the class and cohomology. So anyway, this is to do with this is really a B field transform of this omega minus omega inverse. And you can see that the two form B, when I use it to deform this thing, it does not operate by adding to omega. It is a separate degree of freedom which changes these components of the matrix and leaves this one alone. And for various reasons, when the B field has integral periods, we should consider it to be a trivial type of automorphism and mod out by it. So yeah, this is at the same time, this is equal to, oh, and I can combine these two actually. So you could combine B plus I omega having a class in H2 M C star, because C star is like C modulo Z. This is like C modulo Z. And this is the moduli. Well, it's the tangent space. It's yeah. This is close to being so an open set. This is the local moduli space of GC structures. So the moduli space of the A model is identified with the moduli space of GC structures in this case.
So by A model here, you mean Gromov-Witten invariant associated to, or not?
Yeah. Well, yeah. I mean that's right. That's right. It's the Gromov-Witten theory. It's the closed A model. In both cases, it's the closed A model or the closed B model. There's no boundaries. There's no category. Yeah, that's right. So when you consider, yeah, exactly.
But the construction of the B model doesn't go through this work of Costello, and I thought the B model was a bit more like.
I'm sorry.
So.
Say again.
I think the mathematical understanding of the P model goes through the work of Costello. I'm not sure.
Well, I don't know about that.
Okay.
I mean, I think Costello was interested in the B model with boundary, right? Because that gives the open string theory, the open topological string, right? And that means that it's a category. So the algebraic invariant underlying the A model with boundary is a Calabi-Yau 3 category. It's a category, like the category of D branes, or the category of derived the derived category of coherent sheaves on the manifold. But the closed A model was understood shortly after the paper of Witten. It's a long, it was all done by Giventhal and people like that. So the deformation theory of the A model was known, around the time of Witten, and there was no, with Kontsevich's work on nodal, what does he call them? Stable curves, right? The introduction of stable curves and the work of Giventhal and all those people, even Tian and many people, the mathematical theory underpinning the closed A model was put on a firm foundation, and that was the context in which Costello worked.
So, what do you understand by closed B model then?
Closed means that the surfaces, that the two-dimensional domain of the sigma model is a closed two manifold.
Yeah, but for the closed B model, is it?
Closed B model is the same thing, that the domain is a closed surface, right? And you don't have sheaves at all. There's no sheaves, there's no vector bundles, nothing. All you have is holomorphic maps from a compact curve into your manifold. So, for example, in Gromov-Witten theory, you study. So in Gromov-Witten theory, right? Should I continue along these lines?
Sorry,
you can leave if you want, but so
no. My real question was whether it would be interesting to understand what this B model is for, like a small deformation for a GCS, which is a small deformation of a complex structure. If there is anything
absolutely, yeah, absolutely, yeah. So I mean, this is in a way
I had to know what the B model is before.
yeah. So absolutely. So in a way, deforming the B model is the thing that I've been most interested in for years and years and years. Like all of the stuff that I've been doing on non-commutative geometry and groupoids and all that stuff, all that bullshit, is to study the deformation of the B model in the non-commutative direction, where you turn on the bivector field. So the idea is you turn on the bivector, and from an algebraic point of view, everything is supposed to be the same, roughly speaking, because everything factors through the B model, and the B model doesn't really care about whether it's a complex or a GC structure, right? And so, in principle, the algebraic geometry should be deformed, or this algebra should be deformed to a non-commutative algebra, and the B model should provide it for you. And so, but what I found interesting is that, and this is something that was first understood by Kapustin, okay, but it's something that I have thought and written a lot about, which is that, when you start with a B model and you deform away from the B model, right, then you are not on a complex manifold anymore, really. You're on a generalized complex manifold. Okay, so, and as we saw before, you have a choice of whether to think of that thing as being a holomorphic Poisson manifold, where you are unnecessarily remembering the complex structure, or you could do a B field transform, thereby doing nothing, just it's an isomorphism, an automorphism, and view it as a symplectic structure. So as soon as you move away from complex, this structure has two interpretations. You could either think of it as something holomorphic, in which case you would you would start talking to your algebro-geometric friends, or you could realize that from a GC structure point of view, it's really just a symplectic form, and therefore it's really the A model now. So in other words, it's not just that the GC structures interpolate between, but it's also that the A and B model are actually on a continuum. And to be more precise, the A model is the one that's more important, because the A model is generic. If you start with the B model and you deform, the correct thing, in my opinion, is that you should interpret that deformed thing as an A model. Okay, and so it becomes more complicated. Like like some people in the physics literature at the time, and this never been corrected because they still haven't understood this point, that they were saying that if you take the B model, like the amazing thing about the B model, the reason that everyone loves the B model is because there's no quantum corrections, which means there's no instantons, there's no pseudo-holomorphic curves to take into account. I mean, that's not entirely true, but roughly speaking, it's true, and it's what makes it possible to compute everything in the B model. Okay, but the problem is that as soon as you deform from the B model, that fails to be the case. Even though they want it to continue to be the case. They want to say that when you deform something that has no instantons, then there aren't any instantons. But that doesn't make any sense to me, because the existence of instantons is not an open condition. The non-existence of instantons is not an open condition by any means. So it seems to me that when you deform away from the B model, it really becomes an A model, and it becomes more complicated. And you would need to have a good reason to believe otherwise. Like, for example, if the symplectic form was exact, or if if there was some other reason, then you would have a valid reason to believe that the deformed B model is as simple as the B model. And anyway, that is important, because what that seems to point to is the fact that in order to write down these non-commutative algebras, and in order to do non-commutative algebraic geometry, you should really be this issue of the A model should really come in, and so yeah, that's the suggestion. So that's why, for example, you see I mean, to me, one of the most amazing papers of the last 20 years in geometry is this paper of Oru, Katsarkov, and Orlov, where they use the A model to produce the non-commutative CP2. So they extract the non-commutative geometry of CP2 directly from an A model computation. But yeah, anyway.
Well, so okay, maybe we wrap it up.
Yes.
And I guess so you'll speak next week on generalized Kähler.
Yeah.
And then I guess maybe since Francis is here, can we lean on him to talk about the potential the week after that?
Francis, you're going to give an intro, right? A gentle intro to the potential.
What is the date?
2 Tuesdays from today, 2 weeks from today.
Let me just check. Should be okay. Just check my calendar. It would be the 16th.
That's right. Yeah.
Yeah, I can do that.
Okay, great. Excellent.
Hey, everyone. See you later.
Yeah, thanks again, Marco.
Cheers.